Monoidal categories and their representations, Lecture 5. Problem session. Problem 1. Let G be a group and K a field. Check that the category of all G modules is a monoidal category with respect to the usual tensor product of G modules. Solution. Let's go through the definition of this monoidal category. The category itself is defined as the category of all G modules. The monoidal structure is given by the tensor product over the field, and when we have the tensor product of two G modules, the structure of a G module on this tensor product is given by the diagonal axiom. So if we take an element G in G and apply to the element V tensor W from the tensor product of two G modules, the outcome should be equal to the tensor product of G of V and G of W. The identity object in this monoidal category should be the trivial G module. So this is a G module which is one-dimensional, so it is isomorphic to K as a vector space, and it has a trivial action of the group. So each element of G acts on this module as the identity map. And the rest of the structure, that is the associator alpha and the left and the right unitars, are inherited from the category of all vector spaces. This means the following, that if we apply the associator to the tensor product of V and W and then tensored with U, we will get the tensor product of V with the tensor product of W and U. If we apply the left unitar lambda to the element C tensor V, here C is an element in the trivial G module, so just in K, a scalar, and V is an element in V, the outcome should be C times V. And similarly, rho applied to V tensor C should be equal to V C, and this is again equal to C V. So what we need to check? We need to check the Pentagon Axiom and the Unitality Axioms for this tensor product. Let us recall that the vector space V tensor W is spanned by all elements of the form little v tensor little w, where V is an element in V and W is an element in W. So if we want to check the Pentagon Axiom and the Unitality Axioms, it is enough to check these axioms on the elements of the form V tensor W. So here is a Pentagon Axiom. So we start from W tensor X, then tensored with Y, and then tensored with Z. And our associator just rearranges brackets in this tensor product. And then the second application of the associator rearranges these brackets again. So we do not change the elements W, X, Y, and Z, which we start with. We just rearrange the brackets. And then the second path in our Pentagon axiom rearranges these brackets in a different way, but we started from one bracketing and we end up in the same but different bracketing, which means that these two passes for these particular elements in this diagram give the same outcome. And this is exactly the statement that this diagram commutes. And similarly for the unitality axiom, so if we start from the tensor product of X with some scalar C and then tensoring with Y, we can use the associator to rearrange the bracket to get X tensored with C tensor Y. If we apply the right unitar to the first expression, we get XC tensor Y. If we apply the left unitar to the second expression, we get X tensor CY. But this is a tensor product over the field, and C is an element in our field. So XC tensor Y is equal to X tensor CY. So we get the same result regardless whether we go this way or this way in the diagram. In other words, this diagram also commutes. And this completes the checking of all axioms for the category of all G modules. In other words, the category of all G modules is indeed a monoidal category. Problem 2. Let G be a monoid and K a field. Check that the category of all G-graded vector spaces with respect to the usual tensor product is a monoidal category. Solution. Let us recall the definition of the category of all G-graded vector spaces. So the objects in this category are all G-graded vector spaces. So all vector spaces which can be written as a direct sum over all G in G of Vg. So Vg is the homogeneous component of the vector space which has degree G. Morphisms in the category of graded vector spaces are homogeneous linear maps of degree 0. So this means that we have a linear map F from the direct sum of Vg's to the direct sum of Wg's, and this linear map should send each homogeneous component Vg to the corresponding homogeneous component Wg for any element G in our monoid G. The tensor product is defined as follows. So if we tensor the homogeneous component Vg with the homogeneous component Wh, then we should tensor the corresponding vector spaces V and W over the base field K, and then the degree of this component will be G times H. The identity object in this monoidal category is the vector space which lives in the homogeneous degree E. E is the identity of our monoid G and is one-dimensional in that degree. So we have our field K, which is homogeneous of degree E. And the structure maps, the associator alpha and the two unitors rho and lambda are inherited from the category of all K vector spaces. And we already used the terminology that V sub G is the homogeneous component of degree G. So again, we need to check the axioms for a monoidal category. So we need to check the Pentagon Axiom and the Unitality Axiom. Since each graded vector space is generated as a vector space by its homogeneous components, it's enough to check all the axioms for homogeneous elements. And if we take homogeneous elements and let's say look at the Pentagon Axiom, then we have the tensor product of the homogeneous components WA, XB, YC, and ZD. And we need to look what happens if we change the bracketing and move around using the associators. The point is that any bracketing of this tensor product gives something homogeneous of degree exactly A times B times C times D. And since G was a monoid, this element of G doesn't depend on the bracketing of the factors. But this means that the Pentagon axiom just follows from the Pentagon axiom for usual vector space. Since the degrees are the same, the rest is just exactly the same what we did in the solution to the previous problem. Similarly for the unitality axioms. Regardless of how we bracket the tensor product of XA, the identity KE and YB, it will give us something of degree A times B. And this is also the degree of just XA tensored with YB. So the checking of the unitality axiom will also be exactly the same as the checking of the unitality axiom in the previous example. And this completes the solution. So this problem has an interesting consequence. If G is not a commutative monoid, then the degree GH of Vg tensor UH does not coincide in general with the degree Hg of UH tensor Vg. And this shows that the tensor product in a monoidal category is not commutative in general. So the tensor product of x and y does not have to be isomorphic to the tensor product of y and x. Problem 3. Assume that we have a group G which acts on an abelian group A. So the identity element in G is E, and the identity element in A is 1. And we assume that G acts on A by automorphisms via a group homomorphism chi from G to the group of automorphisms of A. So this should be A. Define the category C, which depends on G, A, and chi, as follows. The objects of this category are symbols delta sub G, where G is an element in G. So the set of all morphisms from delta G to delta H is empty if G and H are different, and the set is equal to A if G is equal to H. And then the composition of morphisms is given by the group operation in A. The tensor product of objects is given by the group operation in G. So tensor in delta G with delta H gives us delta of G star H. Tensor product of morphisms is defined in a non-trivial way. So if we have a morphism A from delta G to delta G and a morphism B from delta H to delta H, then A tensor B is defined as A times in the group A with the element chi of G applied to B. So chi of G is an automorphism of A and we applied to B. Note that this element G is exactly the element where we take A from. So A is a morphism from delta G to delta G. So the identity object in this category is delta E. E is the neutral element in G. The assignment is to define alpha, lambda, and rho such that the whole thing becomes a monoidal category. Solution. Let us first note that G is a group, so the multiplication in G is associative. Therefore, the tensor product of objects is strictly associative. So delta F tensor delta G and then tensor with delta H is just equal to delta F tensored with the outcome of tensoring delta G and delta H. So this is because of the strict associativity of the product in the group G. So because of the strict associativity, we have a choice to define alpha using the identity elements in the corresponding Hom spaces. A non-trivial thing to check, we need to check that this alpha is a natural transformation. So the associator should be a natural transformation of the functor with 3 arguments, with this bracketing into the functor with 3 arguments with different bracketing. So let's check that these identity elements indeed define a natural transformation. Given an element A, which is a morphism from delta F to delta F, an element B, which is a morphism from delta G to delta G, and an element C, which is a morphism from delta H to delta H, the tensor product of A and B, tensored later with C, is equal to the following. So the tensor product of A and B is by definition A times chi of F applied to B. And then when we tensor with C, note that A tensor B has degree Fg. So we should take this element A times chi of F applied to B, and then we should apply to C the element chi of Fg. Fg is the degree of A tensor B. So this is for this bracketing. So another bracketing, A tensor with B tensor C. So we should multiply A with chi of F applied to B tensor C. So B tensor C is B times chi of G applied to C. So we get these two expressions. Note that chi of F is an automorphism, so it's a homomorphism. And so chi of F applied to B times something will be chi of F of B, this thing, times chi of F applied to chi of G of C. And chi of F of chi of G is equal to chi of Fg, because chi is a group homomorphism. So it follows that A tensor B tensored with C is equal actually to A tensored with B tensor C. And this implies that the identity elements which we have chosen for alpha indeed define a natural transformation between the two functors of different bracketing of the triple tensor product. So alpha is indeed a natural transformation, and then the Pentagon axiom is obvious because all maps in that axiom are given by the identities. And so both ways around the Pentagon diagram will be equal to the identity. Okay, so this is about the associators. Now about the unitors. Note that the tensor product of the identity element delta E with any delta G is strictly equal to delta G, regardless of the order in the tensor product. So this allows us to define lambda and rho using the identity elements. And now we need to check that lambda and rho are natural transformations. For A, which is a morphism from delta G to delta G, consider one tensor A when 1 belongs to the identity object. So it's our group A, which is placed in degree the identity of G. By the definition of the tensor product, one tensor A is equal to 1 times, and we need to apply to A chi of the degree of 1, which is E. But chi is a group homomorphism, so chi of E is the identity map. So applied to A, this gives A, and 1 times A is A. Similarly, if you try to tensor A with 1, so A now lives in degree G. So what we should do, we should multiply A with chi of G applied to 1. But chi of G is an automorphism, so it sends 1 to 1. So we get A times 1, and so this is equal to A. And these two checks mean exactly that lambdas and rho are natural transformations. So our choice to define lambda and rho using the identity elements was a good choice because lambda and rho defined in this way are indeed natural transformations. And now the unitality axiom is obvious because all maps in the corresponding diagram are given by the identity elements. So any way around the diagram is just equal to the identity. This completes problem 3. Problem 4. Let G be a group and A an abelian group. Let omega from G cross G cross G to A be a 3 cocycle with values in A. That is, omega satisfies the following equation. For all G1, G2, G3, and G4 in G, omega applied to G1, G2, G3, G4 times omega applied to G1, G2, G3, G4 is equal to omega of G1, G2, G3 times omega of G1, G2 times G3, G4, and then omega of G2, G3, G4. Assume that we have such an omega. Define the category C, which depends on G, A, and omega, as follows. Similarly to the previous problem, objects of this category are formal symbols delta G, where G is an element in our group capital G. And similarly to the previous problem, the Hom set from delta G to delta H is empty if G is different from H and is equal to A, where G is equal to H. And the composition of morphisms is given by multiplication in A. The tensor product on objects is exactly as in the previous case. Delta G tensor delta H is equal to delta G times H. And the tensor product of morphisms is a simplified version, so A tensor B is just equal to AB. So compared to the previous problem, we take chi to be the trivial morphism which sends all elements of G to the identity map on A. The identity object is delta E, and here comes a difference. The associator is no longer given by the identity map. It is given by the identity map times the value of omega applied to the degrees of the components in the associator. So in the associator, we have three components, they have degrees. So we apply omega to those degrees, and we get an element of A. So we multiply the identity map by that element in A. And the assignment is to define the uniters such that the whole thing becomes a monoidal category. So we start by taking a closer look at the Pentagon Axiom. So here is the Pentagon Axiom. So we have the tensor product of W, X, Y, and Z, which is bracketed in different ways. And these ways are connected by the associators. And this pentagon diagram is supposed to be commutative in a monoidal category. So let's look at this diagram and let's look at the equation which defines the three cocycles. So here is the equation from the previous slide. Omega applied to G1, G2, G3, G4 times and so on is equal to the triple product. Let's compare the Pentagon axiom with this equation. So in the Pentagon axiom, we have here the path of length 2, and the first map is alpha, the associator for W tensor X, Y, Z. So we assume that W has degree G1, X has degree G2, Y degree G3, and Z degree G4. Then the value of omega at G1 times G2, G3, G4 is exactly the additional factor in our definition for the associator for W tensor X, Y, Z. Now here we have the associator for W, X, and Y tensor Z, and this corresponds to this factor omega of G1, G2, and G3 times G4. So this is the left-hand side, the path of length 2. And now let's look at this second path in the Pentagon axiom of length 3. So the first error here is identity times the associator for W, X, and Y. So this corresponds to the factor omega, G1, G2, G3. Here in the middle, we have alpha for W, X times Y, and Z. This corresponds to omega for G1, G2 times G3, and G4. And finally, here we have alpha for X, Y, Z. This corresponds to omega for G2, G3, and G4. And so we see that the three cocycle axiom for our omega means exactly that for our definition of the associator, the Pentagon axiom is satisfied. We also know that the tensor product in our category is strictly associative. However, we choose to take the associators which are not given by the identity maps. So what we are really doing, we are defining a different structure of a monoidal category on something which looks as a strict monoidal category. So everything with associators is okay, and we need to define the left and the right uniters. Recall from our general theory that the left uniter is defined using the map I from the Agno definition of the monoidal category as the preimage under tensoring with the identity object of the morphism I tensor the identity after the associator alpha II something inverse. And the right uniter rho is defined as a preimage under the right tensoring with the identity object of the morphism identity tensor I after the associator of something, the identity, the identity. Looking at these formulas, we set that the left uniter evaluated at delta G should be the inverse of the associator for the identity, delta G. And the right uniter evaluated at delta G should be the associator for delta G, the identity, the identity. So let's now take a look at the unitality axiom. So here is a triangle in the unitality axiom. We have here the associator in the top, and then the right uniter here, and then the left uniter here. So using these definitions, this triangle is commutative if and only if we have the following equality. So here for the path of length 1, we have the right uniter, so we have the associator for delta GII, which has a factor which is omega evaluated at G, E, E. So G is the degree of delta G and E is the degree of the identity object. So this should be equal to the following product, which comes from the composition of passes. So we have the composition of two arrows here. The arrow with the associator for x, identity, y gives us the factor omega evaluated at G, E, H. And then the left unitar factor here gives us, from our definition, omega evaluated at E, and H. So H is a degree of y and G is a degree of x here. So our unitality axiom reduces to this equation. And to get this equation, we look at the three-cocycle axiom for the following choice of G1, G2, G3, and G4. So we take G1 to be equal to G, G2, G3 to be equal to the identity, and G4 to be equal to H. And then the three-cocycle axiom gives that omega at G, E, H times omega at G, E, H should be equal to omega at G, E times omega at G, E, H times omega at E, and H. So on both sides, we have this additional factor of omega GEH, which we just delete because we are in a group. And then we can move omega at EEH to the left-hand side with the inverse and get exactly our equation. So this shows that the three-cocycle axiom implies the unitality axiom for our category, and this completes the proof. Problem 5. Let f be a monoidal functor from a monoidal category C to a monoidal category C tilde, with a corresponding monoidal structure given by xi and phi. Let G be a functor from C to C tilde isomorphic to f. Show that for any isomorphism kappa from f to G, there are unique zeta hat and phi hat such that G together with the zeta hat and phi hat is a monoidal functor from C to C tilde, and such that kappa intertwines Z with Z hat and phi with phi hat. Solution. Since we require that kappa intertwines phi and phi hat, we can only define phi hat such that the following diagram commutes. So we have the identity in C tilde, the identity tilde, and then we have the map phi to f of the identity in C, and then we have the identity in C tilde and the equality between them, and then we have our natural transformation kappa from f of I to g of I, so we define phi hat such that this diagram commutes. Note that both phi and kappa are isomorphisms, so phi hat is an isomorphism. Similarly, we also require that kappa intertwines z and z hat, so there is only one way to define z hat, and this is to define it such that the following diagram commutes. So we have f of x tensored with f of y, and then we have zeta evaluated to x and y, and this is a map to f of x tensor y. From f of x tensor y, we can use kappa to go to g of x tensor y, and from f of x tensor f of y, we can use kappa x tensor kappa y to go to g of x tensor g of y. So we define zeta hat as a unique map here such that this diagram commutes. And again, since all other elements in the diagram are isomorphisms, zeta hat is also an isomorphism. So these two definitions immediately imply the uniqueness claims for zeta hat and phi hat. Of course, if we can check that these two natural transformations indeed define on G the structure of a monoidal functor. So let's prove that this defines on G the structure of a monoidal functor. So we need to check one hexagonal axiom and two quadrangle axioms for the unitality. Let's start from the quadrangle axioms. for the right unitality. So consider the following diagram. So we have the quadrangle axiom for f. So we have f of x tensored with the identity. We can go to f of x tensored with f of the identity, and then we can go to f of x tensor with the identity, and then to f of x. And we have a similar quadrangle for G, and then we can use kappa to define maps from the corresponding sides of the F quadrangle to the corresponding sides of the G quadrangle. So in this big diagram, the front rectangle commutes because F is a monoidal functor. This is one of the axioms for the monoidal functor F. The right rectangle commutes by the definition of zeta hat. So this rectangle is exactly the definition of zeta hat. The left rectangle commutes because rho tilde is a natural transformation. We have rho tilde here and rho tilde here. So this is naturality of rho tilde. The bottom rectangle is commutative because kappa is a natural transformation. We have kappa here and kappa here, F here and G here. And the top rectangle commutes if we combine the definition of phi hat, so this is for the second factor, and the interchange law. So for the first factor, we just have kappa for the first factor. So this means that the whole diagram commutes. And then the back quadrangle in this diagram is exactly the corresponding monoidality axiom for our functor G. So let's say the right monoidality axiom is now proved, and the left version of this axiom is completely similar. And now we need to check the hexagonal axiom. So we consider the following diagram. So we have again the hexagonal axiom for F. We write a similar axiom for G. So here it's a back triangle. And then we connect them using kappa. And similarly to before, the front hexagon commutes because F is a monoidal functor. So this is just the monoidality of F. The left and the right lower rectangles, they commute by the definition of zeta hat. For example, in the left rectangle, we have z here, zeta hat here, and kappa which connects them. So directly from the definition, it follows that this commutes, and this commutes similarly. The left and the right upper rectangles, they commute by the definition of zeta hat and the interchange law, because we have an additional factor in both cases. Now the bottom rectangle commutes by the naturality of kappa. So we have kappa here, G of something and F of something. So here is a naturality of kappa. And the top rectangle, it commutes by the naturality of alpha tilde. We have alpha tilde here, and then different bracketing of the same things on the sides. So the whole diagram commutes, and then the bottom hexagon in this diagram is exactly the corresponding monoidality axiom for G. So this checks everything and completes the proof. Problem 6. Let K be a field and A a finite dimensional associative K algebra. Consider the monoidal category of all finite dimensional AA bimodules. Let C be the monoidal category of all right exact endofunctors of A mod. Prove that the category of all AA bimodules is monoidally equivalent to C. Use this to prove that an AA bimodule M has a right, respectively left adjoint, inside the category of AA bimodules, if and only if M is left, respectively right, projective. Solution. So let us first construct a monoidal equivalence from AA bimodules to C. So we have the natural functor W from AA bimodules to C, which takes a bimodule M and sends it to an endofunctor of A mod given by left tensoring with M. And by the Eilenberg-Watts theorem, this functor is an equivalence of categories. So the category of right exact endofunctors of A mod is equivalent to the category of all AA bimodules via this functor. So what we want to prove? We want to prove that this equivalence is actually a monoidal equivalence. So W is a monoidal functor. To prove this, let's first recall that the identity and the functor of A mod is isomorphic to tensoring with the regular AA bimodule A via the multiplication map. So the natural transformation from A tensor X to X given by multiplication, so the element A tensor X goes to AX, is an isomorphism of functors. This defines our component phi in the monoidal enhancement of the functor W. To define the component zeta, we use the usual associator. So zeta should be a natural transformation from W of something composed with W of something to W of the tensor product of the two components. In other words, zeta should be a map from M tensored over A with N tensor over A with something to M tensor over A with N tensored over A with something. We define the map zeta using the usual associator. So we send the element M tensored with N tensor X to the element M tensor N tensored with X. So let's look at the monoidal axioms. So the right unitality monoidal axiom is this square. And if we look at what happens to the elements in these modules under our map, so if we start here, so all maps here are isomorphisms, by the way. So we start here, so we have M tensor with A tensor X, and then we have the multiplication map, which send this element to M tensor AX. So here we have our zeta, which just rearranges the brackets. And here now we have the multiplication map, which sends us to MA tensor X. And here the vertical map, it sends M tensor AX to M tensor AX. Note that the category C is a strict monoidal category, so the right uniters are just the identities. But fortunately, M tensor AX is equal to MA tensor X because this is a tensor product over A. So this establishes the right unitality axiom. And then the hexagonal axiom is actually obvious because both the associators and zetas are given in terms of rearranging the brackets. So if you look at the hexagonal axiom, then for each term we have a certain way to write the brackets on the tensor product of M and K and X. And so we start with one of the bracketings and then we rearrange the bracketings and we arrive to some other bracketing. And it doesn't matter how we go in this axiom, we end up in the same bracketing. So this diagram is also clearly commutative. So therefore, W is indeed a monoidal equivalence. Further, if M is an AA bimodule, then the endofunctor of tensoring with M is always right exact. And so it always has a right adjoint endofunctor on A mod, and by the usual adjunction theorem, this endofunctor is taken home from M to something. This functor is automatically left exact, but it doesn't have to be right exact. So the functor of taking home to something, it is always left exact, and it is right exact then if and only if it is exact. And the functor of taking home from something is exact if and only if the module you take home from is projective. So this means that the right adjoint homing from M to something, this is the right adjoint of tensoring with M. So this right adjoint, which always exists in the category of all endofunctors, this right adjoint belongs to the category of right exact endofunctors, which means has a form of tensoring with some bimodule M, if and only if M is left projective. So now about the left adjoints. The functor of tensoring with M is always right exact. So this functor has a left adjoint if and only if it is left exact. Since it's always right exact, it has left adjoints if and only if it is exact. And the functor of tensoring with M is exact if and only if M is right projective. Note that here we work with finite dimensional algebras. For rings, the corresponding condition should be that M is right flat. Also note that the left adjoint is automatically right exact if it exists, and so it belongs to C. So this means that the left adjoint of tensoring with M exists if and only if M is right, projective. Some further problems and questions. Question 1. Let M be a set with two monoidal structures, M star E and M sharp F. Assume that these two structures satisfy the interchange law. So X sharp Y star A sharp B is equal to X star A sharp Y star B for all X, Y, A, and B in M. Prove that star is equal to sharp, E is equal to F, and that this common operation star is commutative. Question 2. Show that in the previous problem, already the associativity of star and sharp follows, in fact, from all other assumptions. We do not need to assume M star E and M sharp F to be monoids. So we don't need to assume the associativity of the binary operation star and sharp. Question 3. Show that the category of all monoidal categories with one object and monoidal functors is equivalent to the category of commutative monoids. Question 4. Show that the right adjoint of tensoring with an AA bimodule M, so this is an endofunctor of A mod, if such a right adjoint exists in the category of AA bimodules, then it is isomorphic to tensoring with the AA bimodule hom A from M to A. And question 5, show that the category of all AA bimodules is rigid if and only if A is semisimple. So here A is a finite dimensional K algebra. Thank you very much and see you next time.